PreCalc, Thursday the 11th. We're looking at zeros of polynomial functions, and we have to remember what a polynomial is and then what a higher order polynomial is. A higher order polynomial is greater than degree 2. And a polynomial is a function that is continuous. It has no breaks, no jumps, no holes, no asymptotes, no gaps, and it has smooth turns, no sharp turns. For example, y equals the absolute value of x. That graph is not a polynomial. So this is no go. This is a polynomial. So we're expecting a smooth curves, turns, no gaps and holes. We can learn about higher order polynomials we can learn their basic shapes by looking at the lead coefficient. And you had this last year, so it's just by way of reminder. So the lead coefficients, we're going to look at them to determine basic end behaviors. We'll say that. Lead coefficients determine end behaviors. When I say end behaviors, what is this function doing at one end and what is it doing at the other end? All right, so to look at some principles when the degree is odd. Remember, degree is the greatest exponent in the function. So when the degree is odd, it will act very much like y equals x cubed. So we've studied y equals x cubed, and you'll recall that it comes like, here's y equals x cubed. The part we're looking at is the end of it. So it's coming, it goes, and when we get on this side it's going way down, and when we get on this side it's going way up. So every odd function is going to act like that on its ends. So if we have y equals x to the 5th plus 3x to the 4th minus 3x squared plus 2x minus 1, that is degree 5. The greatest exponent is 5. So it is an odd number and it's going to act in the ends like x to the x cubed. So I'm not sure what this function is going to do in between, but at the ends it's going to be going down on this side and going up on this side. In between, I'm not sure what we got going, so I'm not promising you anything in here. I can make you some promises, but what I'm interested in this part of our discussion is the end behaviors. So the end on the right, it will be going infinitely high. On the end on the left, it's going to be infinitely low. So sometimes we say this as x, not x, as x approaches infinity. So that means it's as x values are going this way, what's happening to y values? Y is approaching infinity. On this side we say as x approaches negative infinity, so the values for x are getting closer to negative infinity, then y value is also going down and approaches negative infinity. Alright, so these are ways that we can describe that. Sometimes we just say it's a down up. So it came from down and it went up. Down up. Alright, so let's see what is happening when the degree is even. So degree is even, such as y equals x to the fourth minus 5x squared plus 4. Here we see the highest exponent is a 4, so the degree is even, and we're looking at the lead coefficient. That's the one with the highest degree, just like up here. So we're looking at the lead coefficient to determine n behaviors. So okay, so similar to what our thoughts were up here, when it's even, it's going to act like the basic parent function, y equals x squared. So, therefore, because y equals x squared comes from, or is going up on the left and up on the right, we would expect similar behavior for any even function when the lead coefficient has an even degree. So to act like this one is going to go up on, it's going to be going up on the left and up on the right, and in between it'll probably do something like that. No promises, but again, I'm interested on n behaviors right now. All right, let's talk about what happens back up here when the lead coefficient is negative. Here the lead coefficient was positive. So what if we had a similar situation and we had y equals negative x to the fifth plus 4x cubed minus 2x plus 5. Then this will act like y equals negative x to the third, which will act like the normal one, but here's the normal one dotted in. But when we put a negative sign, we know that reflects it across the x-axis, so it's going to act like that. So it's going to go up on the left and down on the right. So this will do the same thing. It'll be coming from up, or will go up, you can say it either way, and it'll be going down here. So in between, I'm not sure what it does, but somehow it's got to get to going like that. Alright, no promises of what it's doing in here, but in the ends it will look like that. Alright, so what do you think is going to happen when we have the lead coefficient is even but negative? If that's the case, something like y equals negative 2x to the fourth plus 2x squared. Alright, so if the normal function will act like up from the left up to the right, then what will happen if it's negative? It's going to act like y equals negative x squared, which will invert this, reflect that, and we'd have a down, down. So this function will end up going downward on this end, and it will end up going downward on this end. In between, maybe something like that. No promises about the in-between. Again, I'm looking at n behaviors. Alright. Hopefully that kind of thinking looks familiar. And the things I'm going to end with tonight is looking at how we will find the graphs in a little more detail. To do that, we are going to have to find the zeros. And the only way that we're going to have a chance to expand upon this year together is when the function is factorable. So find the zeros of the polynomial by factoring. When it's not factoring, when it's not factorable, you can follow a bunch of other clues to get the zeros, and you've seen those before, and we're not going to get into those again this year. So, suppose you have y equals x squared minus 25. Alright, we already know a lot about this because we know its apparent function is, and that this means it drops 25. But I'm going to show it to you a different way, and I'm going to ask you to look at the lead coefficient. It's x squared, so we're expecting it to go up, and we're going to factor it. It's a difference of two squares. Factors x minus 5, x plus 5. Set it equal to 0 to find where the zeros are. And we got two branches. Set this one equal to 0 and that one equal to 0. We get x equals 5 and x equals minus 5. One here. Alright, so it's going to come down and go back up. Looking at the basic shape and the zeros. Alright, you can check that with your calculator. In fact, I'm going to ask you to do that after each one. So what about if it gets a little more tricky and we have y equals 1/3 x squared plus 1/3 x minus 2/3. Alright, so end behaviors. Again, because this is positive, there's going to be up, up. And so we set this equal to 0 and factor it. Let's multiply by 3. When you multiply 0 by 3, you get 0, x squared plus 3x. No, I had that right. Plus x minus 2. So then that's factorable. Equals x plus 2x minus 1. X equals negative 2, x equals 1. So x equals minus 2 is a 0 and x equals 1. So the parabola looks like that. Alright, let's jump up to a cubic. Let's say we have f of x equals x cubed minus 4x squared plus 4x. Alright, first identify the end behaviors. Since it's cubic, it's going to come from down and go up, and we're going to find the zeros. We're going to set this equal to 0 and factor it. Each of the terms has a common factor of x, so we're going to pull it out. And we get x times x, what's that, minus 2, minus 2. So we have x setting each of these, we have 3 branches. We set each one equal to 0. And look at this, these 2 branches yield the same fruit, x equals 2. When that happens, we call it multiplicity of 2. Like twins. And we will find that that is always a touch. It won't pierce the 0, it will just touch it. So let me show you what I mean. So we got a 0 at 0, and we've got a touch at x equals 2. So it can't pierce the x-axis here, it's going to touch it. So we will come up like this. Let me fix my pencil. The only way I can do that is to come up through this point. I don't know why I can't get a pencil to write this night. I guess it's out of lead. Alright, hang on. I can come up with something else. Here's one. So we come up, go through here, touch this, and go up. Alright, so this obeyed the command to use these zeros. It will only touch this, it will not pierce it, and it will come from down and go to up. Alright, and the last example I will do is, and before I do it, I want to give a secret word to see who's listening to my voice. And the secret word, to get full credit for this video, is going to be carabiner. Alright, I will ask you for the secret word and continue this problem. Alright, now this is raised to the fifth. It's odd, so it's going to act like the cubic function in that it's going to go from down to up on its n behaviors. We're going to find some zeros and make an approximate graph by factoring and setting equal to 0. These each have a common factor of x. Is that factor? X minus x squared minus plus 3 minus 2. Does that work? Yep. 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 Okay. So we have 3 branches. Set each one equal to 0. X equals 0. When you solve this, you get x equals the square root of a negative number. That's not in the real, so we won't explore that branch. And this is x squared equals 2, and x equals plus or minus the square root of 2, which is somewhere around 1.4. Alright, so let's sketch those. We have x equals 0. We have x equals 1.4. Alright, so it's got to come from down, hit this, and hit that. Alright, and so we're going to check our graphs after we do the best we can with them. We're going to check our graphs on the calculator. So let's hope that we did a good job on that. Alright, that is our review of polynomials and their zeros. So bring this and the secret word with you tomorrow and carry on.